Hello and welcome back to the tutorial on how to build a convolutional neural network from scratch in Java. Where we left off last time, I think we just finished backpropagation in the max pull layer. So we're on to our final layer now, the convolution layer. The namesake, the titular character of the convolutional neural network, if you will. So what we're going to go ahead and do is create a new layer in our layers package as we have previously. And we're going to call this Convolution Layer. And Convolution Layer extends the abstract class layer. We're going to get some errors here because we haven't implemented the abstract methods. So let's go ahead and do that. Alright, so before we go ahead and fill in these methods, let's just look at a quick reminder of what a convolutional neural network actually is. So, a convolution. We have an input, we have a filter, and we get an output. We're applying a filter to an input. What do I mean by applying a filter to an input? Well, this is how it looks. Hopefully you're familiar with this if you're looking at this tutorial. So we've got this filter, this kind of window highlighted in blue, that slides along our input from left to right, from top to bottom. And each of these slides or movements corresponds to one output node. What is happening as we slide this over? While we're multiplying the value of the filter here by whatever value it's on top of here, and adding all of those up to get our output. This will return a really high value when in this output when the filter matches the input really closely, and will return a really low value when these don't match at all. And in this example we can see we're using a step size of 2, so each time we try to work out what our next output is, we slide the filter along by 2 steps. Most tutorials you'll look at just show you how to do a step size of 1. I'm going to try to tackle this example where the step size is not equal to 1. The backpropagation gets a lot more complicated, but I think it's really interesting and it will involve a bit of calculus. For the meantime, let's just take a look at this forward pass and we'll leave the backpropagation for later. Coming back into our code, let's create a new function which is going to be our convolution forward pass. And this function is basically going to go in our get output. This is going through each of our inputs, which are our list of input matrices, convolve each one with every filter. So we might get 10 input images and we might have 8 filters. We want to convolve each of those input images with each filter, so that would result in 80 output matrices. These things get pretty big pretty fast. Be mindful of that when you're selecting how many filters you want in your convolution layer and how many convolution layers you want, because they're just basically multiplying out your input for each of those filters. So what's going in here? Well, we're going to create a new array. This is going to be, I guess, our output. And for each of our matrices in our input, we're going to do a convolution. So for each input image that we get here, we want to convolve it with every filter. Now at the moment we don't know what our filters are, so let's go ahead and, before we finish this off, look at the constructor for the convolution layer. So what we're going to want is a list of matrices that will be our filters. We are going to want an integer to represent the size of our filters. This assumes that our filters will be square. And then finally we want to keep track of our step size, so how many pixels we are moving across our image with each operation. We also want to keep track of how big our expected input is going to be, so that way we can tell the next layer what our expected output size is going to be. So I'm going to go ahead and create a constructor. And this constructor is going to have everything except the filter list as input, because we are going to create a function that generates these filters. Just as in our fully connected layer, we had this idea of a seed to generate our filters. we're also going to have a seed in our convolution layer to generate these filters, and that way you can pass in the seed in the constructor and you'll always get the same filters every time. But alternatively, you could randomize the seed if you wanted a different result every time. So let's just create that variable, and we'll just add that to our constructor as well. Cool, so now we've got our filter size and we have a seed, so let's go ahead and generate our filters. So this is really similar to the fully connected layer, except we are going to have multiple filters and it's going to be in obviously 2 dimensions instead of 1 dimension. Let's also take an input for the number of filters that we want. Let's go ahead and create a function here called generate filters. Alright, so because we've got all of our other variables set in our private fields, that's the only input we need. So let's create an output array list. Let's get our new Java random number generator. And then for each of the filters that we want to generate, we're going to create a new matrix for our new filter. And then we're going to populate each element in this matrix with a random variable, so a random number between -1 and 1 on a Gaussian distribution. And then set that to the value at our current new filter at I and j. Awesome. And then after we've populated everything in that filter, we're going to add it to the list. And then finally, we're going to set our filters to be equal to filters. Sweet. So let's do that in our constructor. Awesome, so now we have some real filters. So, coming back to our convolution forward pass, for each input, we want to convolve it with every filter. So let's iterate through our list of filters. And what we're going to add to this list is the convolution. So we'll create this function in a second, but the convolution of our current filter that we have, our current input that we have selected, with our current filter, and then along our current step size as well. And then once we've convolved all of that, we will return our output. So let's get in here and define our convolved function. So we'll go ahead and create that method. So first things first, we want to get our dimensions of our inputs, outputs, and our filter all sussed out, so we don't need to do maths every time. So the number of output rows. Alright, now the reason that we don't just use our output rows functions to get our output rows, so for example these functions here, is because we actually use this convolve method in backpropagation as well, and we're actually not, in that case, going to be working with the same dimensions. So don't worry about that now, but that is why we are defining this based on the input in this particular call of this method. Sweet, and so now let's create an output matrix that is the size of our output rows by output columns. Now we're going to want some indices to keep track of which part of our output we are currently writing to. So just as a reminder, indices to keep track of this. We're going to have our output row and our output column. So here it's output row is 1, output columns 1, output row is 1, output row is 2, etc. So as we move this around, just incrementing those to keep track. Cool, so obviously those both start at 0, we're starting in the upper right corner. You'll notice in my diagrams that I've been showing, I've been starting at index 1. Obviously when we're coding we start from the first index is 0. So now we're going to move our filter across the image in the x dimension or in the rows dimension. I guess if we're moving in rows we're moving down. I don't know, it gets confusing, don't think about it too much. And then we're going to be moving in the opposite direction, so across and then down. Spelled step size wrong here. What this is saying here, from our 0 input, and while I is less than basically the edge of our filter, so we're moving our filter right up to the edge, and each time we're adding our step size. So this is our input length minus the filter. So as long as we can add one more filter's worth of length to wherever our current index is, we're good. We don't want to move the filter outside of our input. Alright, and for each time we are incrementing our row, we want to set our current column to 0, which makes this kind of redundant. Well, I guess we'll let it sit there. And then we want to move down our image, increment the columns. So now that we are at a position, so this, you can think about this as where the top left corner of our filter is going to be applied. So for example, we're here, and then we'll increment to here, and then we'll increment to here, and then we'll increment to here. So once we're here, we want to apply this filter around this spot. So more for loops within for loops. That is a lot of this neural network stuff. So for each row and column of our filter, we are going to multiply the filter value with the input value that is at ij plus the index of our current filter. So what we're doing now is adding the index of our filter to whatever the index is of our top left input value. So remember, the top left input value is being incremented by the step size each time we do an iteration. And we are just adding the filter indices to figure out which input we are multiplying by that filter at that indices. Hopefully you'll see what I mean when I do this in code. So figuring out what index of our input we are multiplying. Our input row index is equal to our I plus our current x of the filter, so x corresponding to the filter index and I corresponding to the input, top left input index, and same thing for the row. The column, sorry. Cool, and then we are going to add to a sum. Obviously we're summing this up across the whole filter multiplied in that spot, so for each time we increment where our input is going from, each time we apply that filter, we're going to set our sum to 0 for that location. So let's get our value. So each time we multiply to get this value, we will add that value to the sum. What is our value? Well, it is just our filter value at xy multiplied by our input value at input row index and input column index. And then sum, we just add that value. So once we've done this for each filter value around that location, we're going to put that sum into our output. And then we're going to increment our column here. And after we've done this whole column, we're going to increment our row. And then once we've done this we've moved across the whole input image, so we've gone across and down, we are going to return our output. Alright, so now we have our convolve function on our input, filter, and step size. And this is going to happen for each of our input images with each of our filters. So let's pop this in our getOutput function, which we have to do for all of our layers. So we are going to do our convolution forward pass. And then we're going to pass down to the next layer. And that is all for this method. Now, when we get this vector input, first we want to convert it back into our list of doubles. Vector to matrix function wants the length of the list of matrices that we're spitting out. It wants the number of rows of each matrix and the number of columns of each matrix. So this is just equal to our input in length in rows and our in columns. Sweet, and then we're just going to call getOutput on our matrix input. So just calling back this function. So now we may as well fill in these getOutput lengths, getOutput rows, getOutput columns, and getOutput elements so that our next layer knows what it is receiving as input. So for getOutput lengths, we've kind of already discussed this. We're going to return the number of filters multiplied by the input length. For the rows and columns, we're kind of used to this by now. Our output dimension is the input dimension minus the filter size, and then that divided by the step size, and then we add 1. And then for our elements, we're multiplying our output rows by our output columns by our output length. Easy peasy. So that is our convolution forward pass. Join me in the next one to tackle the big daddy, dirty math, fat calculus subject of the convolution layer backpropagation. Hope you're looking forward to it, and I'll see you